Hello everyone, this is Rui PCB, your trusted PCB partner. Today our topic is beyond 4-layer boards, 6-layer boards, why do we need more layers? In previous videos we have already explored in depth the powerful capabilities of 4-layer boards in addressing complex and high-speed designs. But have you ever wondered, when designs become even more complex, signal rates get higher, and component density increases, even 4-layer boards may reach their limits. That's when 6-layer boards come into play. Today, let's talk about why we need to go beyond 4-layer boards and choose 6-layer boards and what core advantages they can bring. Let's take a look. This PCB here is a 6-layer board, and as you can see, its density is very high. It has two components with one-line packaging. We can see that, for example, its GDP, it has two components with BGA packaging, which means its component density is extremely high. So, in what situations does a 4-layer board start to fall short? Do you still remember the structure of a 4-layer board? It's signal, ground, power, signal. This kind of structure is excellent, but it still has its limitations. First of all, routing space is still tight. Although it's much better than a double-layer board, there are still only two signal layers, the top and bottom layers. When facing ultra-high density designs, such as multiple BGA chips and a large number of electronic components, routing can still be very difficult, sometimes making it impossible to complete all the necessary connections. For example, with this PCB, as you can see, the density on both the front and back sides is already extremely high, and with these two BGAs, it's very hard for a 4-layer board to handle all the routing. Another limitation is the spacing between the signal layers and the reference planes. In traditional 4-layer boards, usually only the outer layers have signal traces, and they are adjacent to the reference planes. The top layer signals are next to the ground plane, and the second and third inner layers, although not commonly used for signals in 4-layer boards, if needed, are usually farther from the signal planes, which leads to less effective impedance control and signal integrity compared to the outer layers. Next is the issue of insufficient isolation. Although the ground plane and power plane provide some isolation in extremely sensitive signal scenarios, such as ultra-high-speed digital or precision analog designs, relying on just two plane layers may not be enough to fully isolate different signal paths. Finally, there are challenges with power integrity. If you have a power plane with multiple voltage rails or high current demands, you may need to implement complex splits, which can affect the integrity of the power plane. For example, as we discussed in another circuit last time, its power plane was split left and right. So with a 6-layer board, you can use a complete plane. What kind of superpowers does a 6-layer board offer? A 6-layer board adds two internal layers to the 4-layer system, resulting in a qualitative leap. Let's first explain the structure of a 6-layer board. This is the structure. There's a top layer, then four middle layers, 1, 2, 3, 4, and finally a bottom layer. So there are two additional layers. First, there's greater routing space. A 6-layer board typically provides four signal layers, such as the top layer, bottom layer, and two internal signal layers. This significantly reduces routing density, allowing us to arrange more signals within the PCB, greatly improving routing efficiency and signal integrity. This is especially suitable for complex BGAs. The second point to consider is that it is able to offer considerably better signal integrity as a direct result of providing a greater number of reference planes. A 6-layer board can usually be designed so that most, or even all signal layers are adjacent to a dedicated reference plane, such as a power plane or ground plane. This allows for better controlled signal integrity and reduces the main causes of reflection. It also enables more effective isolation, as the additional planes provide stronger isolation capabilities for separating different signal types or reducing interference. This is easy to understand. Let's suppose if the inner layer, say L1, is a ground plane D, and the next layer is a signal layer, and then the following layer is again a ground plane D, then this second middle layer can be completely isolated. It won't have any related quality issues, as both sides are fully isolated by complete ground or power plane. This setup can then provide better power integrity, allowing for the design of a superior power distribution network. For example, you can have multiple independent power planes or wider ground planes, which in turn enables more stable planes along the signal paths. Ultimately, this can improve EMI and EMC performance. More planes mean stronger plane capability and more stable reference techniques, which help further reduce EMI and enhance EMC performance. This is easy to understand. With more plane layers, the power and ground layers increase by 2, or even both layers can serve as power and ground, or one layer can be used for internal signals and another for internal signals as well. The core idea behind 6-layer board stacking is not just about simply adding more layers. More importantly, it's about how to effectively allocate these functions. The main concept is to provide more signal routing channels while ensuring that each signal has a complete reference plane, either GND or power, thus delivering excellent signal integrity and low impedance current paths. Through smart upgrades, we can insert ground planes between different signal layers to achieve better electromagnetic compatibility and separate different signal types, such as high-speed digital signals, low-speed digital signals, and analog signals, to prevent them from interfering with each other. Today we explored why, in some extremely complex and high-performance designs, a 6-layer board becomes a superior choice. It offers greater routing space, enhanced signal integrity and power integrity, and enables stronger isolation. Understanding these advantages is the reason we can make the right decisions in advanced PCB design. If you enjoyed this video, please subscribe to my channel for more content. Thank you, everyone.